For the invitation. And so let me tell you something we sort of started a year or two ago, and about the random matrices. And this is a joint work with Lasse Erdős in Munich, and with Benjamin Schrein, and he's here at Cambridge. So the question is, now you take a random matrix and H equal to Hjk. Let's just take a Hermitian case, and now each individual element is distributed according to IID random variables xjk plus I of yjk, and divided by 1 over square root of n, and this diagonal element. Anyway, it's not that important. And now all of them are IID random, independent distributed random variables, and we take the density is e to the minus g of x, and then you normalize the expectation to be 0 and variance to be 1/2, just to this is standard normalization. And if you take the g of x is a x squared quadratic, then this is a Gaussian case, and then you have this GUE model. Now, if it's GUE, of course, you know a lot, but even if it's not GUE, you know the spectrum is between -2 and 2 and plus some small corrections. And then you know that this is correct for many other cases. And not just that. So you look at all these n eigenvalues and this distribution given by the semicircle law, and then you can see if you the spacing, the typical spacing would be 1 over n. And so now the question is, we're asking is, now this eigenvalue distribution, there's a famous this Wigner-Dyson statistics, and there's a level repulsion, and then there's another question is if you know the eigenvector is delocalized. So let me say more precisely, give a definition of what we are talking about. If you compute a number of eigenvalues in the interval I, you denote by n of I, and then the smooth version of density of state usually is defined by the take a trace of Green function with width eta and divide by 1 over n. You have to divide by 1 over n because your density is there are n eigenvalues, so divide by 1 over n, and then this is the sort of smooth version of density of state. It's very close to the density between minus e minus eta over 2 and e plus eta over 2, but it's not exactly the same. But anyway, so the standard theorem says if you take expectation, or you take then divide by n, and of the interval I is given by the semicircle law, and integrate over this interval I. The only thing, the question we are trying to ask is how small can you make this eta? And then mathematically, you also has a precise result about the fluctuation, and then this convergence is not just expectation. You can say almost sure, and so the question is not really in what sense you can prove this convergence. It's really what's the smallest window you can do to prove this is correct. So then what we know mathematically is the following. It's if you take actually you don't know anything about the general Wigner matrices. What you know is if you take no matter this is GUE or GOE, and then they extend this to some other models, but all this work, actually all this rigorous work, Dyson or Dive or Johansson and so on. I mean, there are tons of people here. So what they did is they first diagonalized the random matrices, and then once you diagonalize it, then you get the one-dimensional statistical system, and this one-dimensional statistical physics system has a Gaussian which is x squared, but in general you replace x squared by a potential v of x, and they can do a very large number of class if you change the if you change this x squared to v of x, and there's for large class v of x, you can do it. But I think it's fair to say that all this method based on orthogonal polynomial is really a method on a one-dimensional statistical physics system. You have one-dimensional distribution of eigenvalues, and there's for general class eigenvalue, you can do it. But it's not exactly dealing with the matrix itself. So what we are trying to do is, we're trying to prove the semicircle law of any scale bigger than n to the minus 1. And then we want to prove the eigenvectors are not localized. So here is the statement of the theorem. So you have to fix some small parameters. And now eta is the width of window. So here we take log n divided by n, and log n to some power. Later on I will comment about this width. And then as n goes to infinity, we find the probability if you take energy in the bulk, we have to stay away from the edge of the spectrum, because the edge of the spectrum is always slightly different, and it requires different method. And I think if you're really just interested in the edge of the spectrum, you can try to use moment method. So I think that it's more well, at least, okay, anyway, this is what we did is we stay away from the edge of the spectrum. We look at the number of the eigenvalues, and this divided by this width times n, and this is the density, minus the Wigner semicircle law. And if this is bigger than epsilon, then the probability is exponential minus some constant log n squared. And then, so because this log e to the minus log n squared, so this is very, very tiny numbers. So this is about the density of state. And about the eigenvalues, what we know is, suppose you take any eigenvalues. If there exist eigenvalues with, once again, the eigenvalue has to be away from the edge. Then if L infinity norm, meaning that if there is one component bigger than square root of n times some log numbers, then again the probability is exponential small. And sorry, it's exponential minus log n squared. And so this is the main result I'm going to tell you today. And let me just comment about this log n. I think we can remove this log factor by changing this log n to the eighth power by some constant, which is large, but still has to be large. We cannot go, if you want to do, at the end you want to go to a 1 over n and much smaller, then you need some different statement. That's different. But I think we can remove a log. But the reason I didn't put it on as theorem is because we did it last week, and so while we were here, and I mean, it could be wrong. Okay, so this is the result. Now, as you mentioned, there are some previous results. Actually, the Bai did a lot on these problems, and he did quite a lot on the theorem of one. And I mean, it's not exactly the same, but he did quite a lot, and also this Coulomb-G. And I think anyway, that what they can do is something like 1 over square root of n. That's the best scale they can do. And also, there's work by Gionit and Zaitouni. They are trying to calculate the fluctuation of density of state. I mean, it's actually a funny result. It's they say the fluctuation of density of state vanishes if eta is bigger than n to the minus 1/2. But they don't know what the density of state is. So in order to apply their theorem, they have to use the, their theorem is only a statement about fluctuation. They didn't say anything about density of state. So in principle, what their result is has nothing to do with our theorem, but actually it's related. So
you're saying all previous work required eta to be the width to be the
Square
root of n and nothing
Yeah.
near 1 upon n, which is what you'd like to have.
Yeah. I mean, we didn't really know all this, but after we work more and more, we find out more and more papers and find out actually it's basically all the mathematical work start at 1 over square root of n. So now, the assumptions, we need the g double prime is less than infinity. Remember, we have e to the minus g, so g double prime less than infinity. We also need that it satisfies log sovereign inequality in the following sense, in the sense that u log u, the nu is less than constant times gradient squared of u squared. This is called log sovereign inequality. This constant c has to be finite. Now, I think I want to mention this condition 1, actually Bourgain has different proof. We only use this in one lemma, and he produced a proof that without using this condition. And he requires some cutoff of the random variable. But I think all this is not very important. I think at the end, all this condition will all disappear. But this one probably will stay.
What does that second condition really mean?
The second condition, what it really means is if it's quadratic, and you allow some perturbation, but asymptotic, you sort of, you don't want to be, if asymptotic like 1 over x to the, asymptotic is like e to the minus x, let me see. You know, if asymptotic is like e to the minus x 3/2, then it's not going to be okay. It doesn't work. But log sovereign, if this, it's okay. And then you can plus any bounded term. Any bounded term, you can do it. And I think there are lots of other examples, but this is what. I think for one-body potential, its basic is this. You have to be faster than quadratic.
You have to have an x squared, and
yeah.
then you have to
yeah.
have some other term,
yeah.
which is
yeah.
somehow, well, I guess
I mean,
more.
You need a little bit of this, and the rest is okay. The rest, it doesn't really matter. And so, okay, I mean, maybe at the end one can remove all these conditions, but.
Could you imagine doing something compact support or?
Yeah. Yes.
Okay.
Yes. Complex support is also this one with complex support is also correct. Yeah.
Yeah.
It just depends on the support your size, so it's also okay. So this case of boundary random variable, this two is automatic, correct. I mean, if you have a measure in one dimension, the log sovereign is not a series condition, but the dimension is very large, then it's a series condition, typically. So. Okay, so the rest of this talk is I want to explain you the proof because the proof is sort of very simple, and I can explain this in a seminar. I think the most important idea is this lemma is the upper bound of the density of state. So let's forget about all these technical conditions. Just you take any interval is bigger than log n over n, and once again, this log n now is not important. But in this argument, I'm showing you this will be important. So the probability the number is bigger than some constant times what it should be, n times I, then it's exponentially small. And this is large deviation result. It says the density basic has to be equal to n times the length of the intervals. Now, so the idea to prove is the following. So you write the matrix as in this way. So this is a column. You take a row, and this is a column, and this H is just one element, and the B is n minus 1 times n minus 1 matrix. So this is B is n minus 1 times n minus 1 matrix. And then, so here is just a notation. You use the lambda alpha and u alpha for the eigenvalues and eigenvector of B. And then you define an element. You define a symbol called Xi alpha. This Xi alpha is A dot, the inner product of A and the u alpha, and the inner product square n times n. Okay. Then you can see that if you compute the expectation of Xi alpha, so if you expand this, and because A is remember A is 1 over square root of n. So when you square is 1 over n. Then when you square 1 over n and 1 over n and n cancel, so you get L2 naught of u. So the expectation is 1. So this is correct. Now, so this is just a notation. And the important thing is now if you take this matrix, you calculate green function, at the 1 component, and then you find that this is h minus z. So green function at z h minus z is this little h minus z and minus this vector a inner product with the green function b minus z inverse n times a, and this is also there's a dot here. This is also inner product. So this is just the inverse of 2 by 2 matrix, and so so you just do it and you automatically you get it. Now the last term a dot green function of b inverse a, you write in the following way. So because I know the green function.
Could you go back for just a second? So you have the u alpha are eigen and the lambda alpha also, right?
Yeah, u alpha. Sorry, this English is not right. U alpha is the eigenvector, and
okay.
lambda alpha is the eigenvalues.
That's what I was hoping. And then, but these are random because you have randomness in the beats.
That's right. That's right. They are random. That's right. So everything is random here. Okay. So then you get this formula h minus z minus a dot b minus z inverse of a, and then you use the eigenvalues here. So you get lambda alpha minus z. You get eigenvalues, and then because your green function, then the top would be eigenvector. So eigenvector inner product with a. This will appear. And this eigenvector inner product with a here, and eigenvector inner product with a on both sides, so it becomes absolute value squared. And then I times n because I want normalization to be correct. So this is times n, but I divide by n here.
So you just re-express the Green's function.
Yes,
in terms of
yes,
law.
yes. Just express green function in terms of eigenvalue and eigenfunctions. So this is it's all right. It's all right. And then so now the green function would be less than just the imaginary part of this expression. Okay. Now, imaginary part of this expression, if you calculate, the imaginary part is eta plus eta over n summation alpha times this lambda alpha minus e, because the z is e plus I eta. So lambda alpha minus e squared plus eta squared c alpha. Okay, and then this is just calculations. And then the only thing, I think the only actually the only important point here is the sign here is a plus. So if the sign here is minus, then everything would be horribly complicated. It would be impossible to do. I think the only reason this approach is possible is because this sign is plus. If this sign is plus, and then this means these two imaginary parts, they are enhancing each other. So then you get the following inequality is now you just look at this alpha inside this interval I. And then I can even drop this term. And then inside this interval I, this lambda alpha minus e would be eta squared. So the size of this would be eta squared. Eta squared divided by eta is 1 over eta. 1 over eta you write upstairs, and is eta here. And this n comes from this n. So it's n times eta times this number. Okay. So then you find the green functions at 1, 1 is bounded by this number. And now you average, instead of 1 and 1, you take average of, you take summation over this index. Instead of 1 and 1, you take any j and j and sum over j. So left hand side, so you find that the trace of the green functions, and you times eta, just to make all the normalization, make it correct, this becomes a number, will be less than, so this number, because this gjj is less, this g11 is less than this, then this one become a summation. So now the summation here, what you should notice is, so here I write c alpha, but this c alpha actually has a superscript 1 here, because this is depending on this 1. Okay. So if you write it carefully, and don't worry, I assure you that this is just simple. This is very simple calculation. This number of eigenstate at I is bounded by this number. It's n times eta squared summation k from 1 to n of this number c alpha k, and with the condition that lambda alpha k belongs to the interval I. So now this actually, this is just a straightforward calculation. I think you may not be able to follow all this exponent, but but just trust me, this is come out correct. Okay. So now, if I want to know the number of eigenvalue is bounded from above, the only thing I have to know is that this number has to bounded below. So I have to know this number C alpha k is bounded below. Okay. Now, how do I show that this number is bounded below? They come from two ingredients. One ingredient is the following. This, I think this is well known, but anyway, you will, once you play with this decomposition, you will find out that if the eigenvalue of H, you call it mu alpha, and the eigenvalue of B, you call it lambda alpha. You find they are interlacing. There's a very strong interlacing property. The mu, between any two mu, there's a lambda. Between any two lambda, there's a mu. It's interlacing property. So the number of the eigenvalue of H and number of eigenvalue of B is actually almost the same. Its difference is just by 1. Okay. So now the key assumption, now the key point here is, now let's make the following assumption. Suppose this C alpha of k, now this k is fixed. It can be 1 or 2. I mean, later I will just fix this to be 1. Suppose you sum over C alpha of k, because each C alpha, remember C alpha, the expectation is 1. Remember each C alpha expectation is 1. So if I can think about each C alpha, I just replace by order 1 object, then this summation would be bigger than the number of the eigenvalue of lambda alpha in this interval. So here's let me write here. I think maybe you don't remember, it's expectation. Oh, very good. Expectation of C alpha is equal to 1. So then you replace the C alpha by 1, and if you replace the C alpha by 1, then this summation of C alpha it just become the number of eigenvalues. And the number of eigenvalues, it doesn't really matter it's number of eigenvalue for lambda or it's the number of eigenvalue for mu, because they are interlacing, they are basically the same. Okay? So the question is whether, and if this is correct, then this number would be the number of eigenvalues, and then you get a number of eigenvalues bounded by, this will be n squared times eta squared divided by number of eigenvalues. So then you get the number of eigenvalues bounded by n times eta. So the key here, the mathematical thing you have to do is you have to show that you have a random variable C alpha, and this C alpha, the expectation is 1. Then you want to say that what's the probability that the summation of this C alpha is bigger than this number of this alpha. Okay. Now, if C alpha is IID, if they are independent, then this is obvious because you have to take a k. Suppose you take k random variables, then of course you take a summation is bigger than k, and this if it's not bigger than k, this large deviation event will be very small. But on the other hand, these C alpha are dependent. These C alpha are dependent because you can look at what the C alpha look like. The C alpha look like it's A times U alpha, the inner product. So it's AJ of U alpha of J, summation over J. So when J change, when alpha change, because this U alpha change, and then because A, now you start to correlate each other. And of course, there's a special case. If we are dealing with a GUE, then you find this C alpha actually independent. And that's why it makes GUE much, much easier. So here, now I don't know that the C alpha is are independent, but still there's a lemma we can do. It shows that it doesn't really matter. So it shows that if the summation of C alpha is less than some, suppose your alpha runs through an indices A, and if the summation less than small constant delta times the number of A, then it's exponential minus here. This is again some large deviation result. And this is correct, but this one I think I will not be able to show you the proof. It's not very long. It's actually just if you based on Breskam-Leib's argument, it's just about a page. And Bourgain's proof is probably 2 pages. But so roughly speaking, the general statement is the following. Actually, what one realizes is this actually is a complete general statement. You take a random variable z1 to zn, and they are complex. There's also real versions. You take any projection operator into of rank m. So this is just a projection. P is a projection operator rank m. Then you find the exponential of constant projection operator on projection on z of this rank m projections. Then it's less than e to the minus constant times m. This m is a rank. So this is it means if you take IID random variables and you can project in any direction, then basically it behaves almost like independent. At least in the sense of large deviation that you care. Okay.
You're not assuming any independence at all, right?
No, the z itself has to be independent, but this
z's are independent.
But this p the projection direction can be twisted, because if you think about this u alpha j is eigenvector. Let me see. Can I go back? Here. You see that you make this decomposition here. So this A is from here, and now this B, this U is eigenvector of B. So you talk about probability in A, you can think about B is fixed. So then, am I correct? Yes. This is not right. Yes. So in this case, then this U is this projection is independent of this IID random variable. But actually, this is exactly what's happening here. This U will create some correlation between this A. But
that's the projection.
Yeah, but there's a projection. Okay, so.
No, this C prime depends upon C.
Yeah, C prime will depend on C.
And they both are independent of M.
Both are independent of N. That's right. That's right. Both are independent of N.
And M.
Yes, that's right. Independent of M and N. That's right. Okay. So I think right now we have some, because in the beginning you don't know how big the size of this U alpha. You cannot really do perturbation calculation because the sum of this U alpha may be large. But I think after our theorem, then you can start to think about more perturbative argument, because now the U start becomes smaller, and there are slightly different approach. Once you know that this U is not too big. Okay. So this gives us the proof of the density is not too big, and usually this is it's very important ingredient if you are doing in the analysis. It's once you have a bound that it cannot be too crazy, then usually it helps a lot. Okay, so now what's the proof of a semicircle law? The proof of semicircle law is now this is a Green function and called a Stiger transform of the density, and it satisfies equation of this m plus 1 over m plus z equals 0. This is equation for this m. And this equation is stable in the sense that you put a small perturbation, then the solution will be a small perturbation from the semicircle law. Okay. So now let's look at the Green function. This was the Green function we start with in the beginning. And then you let m of k is a Green function of the case minor. The case minor is you remove the case column and case row. Then again we did exactly the same thing. Is you compute the Green function, taking the summation, and then you use this formula I just mentioned in the beginning, and now you realize this object now here, this AK, BK minus Z of AK. So this one previously becomes C alpha, and now let me define the object. This XK is AK dot 1 over BK minus Z of AK. So let me subtract its expectation and plus its expectation, because when I subtract its expectation is you change this number to be 1. So once you change this number to be 1, it becomes green function of the case minor. And then the error term will be the price you replace this Kc by 1. And this is what we do previously. You replace the Kc alpha by 1, and this is the price, and this is what the price here. So this xk is measure the price you pay. And then, so the formula becomes m equal to this, and this xk is the error term from replacing this Kc alpha by 1. And then there's a 1 over n. This 1 over n is because there's one is n by n matrix, the other one n minus 1 by n minus 1. So it's not very important here. Okay, so you get this formula here. And once you have this formula here, then the next, yes. Then the important thing is now you realize this mk. Again, by interlacing property, this m and mk, they differ very small. So you can replace this mk by m. So you get m equal to 1 over n of m plus z. And now this xk, you have to show that if this xk is large, the probability of xk is large is small, and then you get this equation. And once you get this equation, then we know that the equation of the fixed point for the semicircle law is stable. Then you know the solution of this equation will be close to semicircle law, and then you finished. So the only thing we have to show is the probability for this xk to be large. I mean, it's not large. I mean, xk to be a little bit is not small. It has small probability. And then the lemma says if xk is bigger than epsilon, it's less than exponential minus constant epsilon log n squared. And you see, I mean, here I should explain something. Is here why we choose log n squared. We choose log n squared because this number is less than 1 over n, much smaller than 1 over n. Because if I know if I know one xk is small, it's not enough. I have to know all the xk are small. So I have to sum over all the probability of xk small. So if each one small is by this, and then I sum over all of them, because this is much less than 1 over n, and so even after I sum over all of them, it's still small. And then, if you want to do the case, if you want to remove the log, then the probability of this one small will be less than e to the minus k. But if it is less than e to the minus k, if you sum over all of them, then you're in trouble. Okay, so there's so the reason you take a log is because now you take a log is easier because take a log you can sum over all the possibilities still small. But if you don't take a log, then here you have to fight, because then you start to fight the dependence of xk and xj, and then this will be a problem. Okay, so anyway, so let's focus on this case, but then this will be small, and then this will be all right. And so the only thing I want to show this lemma in the case of log n. Now, I should also mention one thing is if you look at these equations, and in the beginning we got a lot of troubles. We look at this equation as an equation for a random variable here. So as an equation for random variable, because of stability, then automatically say this m is small. Although here say m is close to the semicircle law. In the beginning, when we tried to approach this problem, and I think this was all the previous approaches, we always try to replace the m by its expectation. Now, if you replace m by its expectation, then you have to worry about the variance of m is small or not. But the variance of m is small, you can only establish up to square root of n. And then you immediately have trouble. And so actually, it's better to use the equation directly and use the stability of equation and identify m directly as a random variable. It's a constant, instead of worry about its fluctuations. So let's, okay. Now, okay, so I think I still have somewhere like 10 minutes. So let me try to tell you the second part of eigenfunctions. So the eigenfunctions, they are, because if the eigenfunction L2 norm is 1, if you want to say it's extended, then roughly speaking, each component is about the same. And you can calculate LP norm, would be like that. And then actually one reason we look into this problem, it was Tom, actually he mentioned this in the York's birthday. Say, well, can one prove this L4 norm, for example? Can one do it? And I also learned that in the seminar last week that one can even calculate very precise law for these eigenvalues. And so right now, so of course for us we will have to first understand why it cannot be big, and before any of these calculations can be very rigorous. So our theorem says that if this V is large, then it has more probability. And then if we can replace this, I think we can replace this by some number K. It's fairly close to, but it's at least close to a region that you would like to establish some more precise law. But on the other hand, it's still far because we don't have any precise, we only have estimate, we don't have any precise number. Okay, so now the idea of the proof, it's also this decomposition. It just uses in slightly different way. Suppose you look at eigenvalue equations, HV equal to mu times V. Okay, I actually like this proof quite a lot. It's so simple. And now this V utilizes two components, V1 and W. And W is the raised to n minus 1. And then you look at this equation, HV1 plus A dot W equal to mu times V1. And the other one is A times V1 plus B times W equal to mu times W. These two are the eigenvalue equations. Okay, so for an eigenvalue equation, you solve the second one. Then you get W equal to mu minus B inverse dot A times V1. Okay? Then you take this one, you plug it the first equations, because if now you get W it's not. W equal to this number, but you know the normalization is W squared plus V squared equal to 1. So the W squared is mu minus B minus 2 times A squared. So if you calculate this W squared, you will see you involve mu minus B squared and also involve V1 squared. And then because you involve V1 squared, so you solve the V1 squared. So you can solve the V1 squared in turn. This is exactly equal to this. And this is just a simple calculation. It's 1 divided by 1 plus 1 over n summation of alpha. And because this is mu minus b, this minus 1 will be squared, so it's minus 2. So it's mu minus lambda alpha squared. And then the number here, this numerator C alpha, again, is the inner product between A and this vector V. So again, you find this C alpha here. So it's the inner product between A and the eigen function of B. So you get C alpha here. So this is very similar to the previous expression of Green function, except that here you have a square here. And now, so now what you need is the only thing you need is now you plug in your information about the knowledge of eigenvalues. So you take an interval, of Windows eta, and then you find that inside here this mu minus lambda alpha is just becomes eta squared. Well, here I write as a q over n. Sorry, I write as a q over n. And if you calculate this number would be q over n squared, and then there's 1 over n here, 1 over n here, q over n squared, and this is the number of eigenvector here. Now here you plug in your information that you know that with very high probability, this C alpha summation over this interval is bigger than the size of this interval. And then you plug in all this information, you put it in here, then you get this V1 squared less than q over n. And so that, roughly speaking, the L infinity norm of V is n to the minus 1/2. And I mean, this q is some log. I just neglect all this log. So this is the argument.
That's very much like the proof you gave for the precise, the short distance fluctuation, no, not the fluctuation, just to control the density of states at small scale.
Yes.
It's almost the same proof, right?
Yes, it's almost the same proof, except that you just change the Green function to these eigenvalue equations.
Yeah.
And the eigenvalue equation, then you solve W in terms of V, and that's it. And so, I mean, this part is now is still simple because the main reason is because you don't have a space structure. If you have more space structure, this part would be much harder because now what we say here basically is just count the number of eigenvalues, and it automatically tell you about eigenfunctions. But once you start to do band matrices or whatever, then you start to worry about locations. Okay, so this is this part of argument, and so everything is a large deviation argument but I should say, if you want to remove a log, it's actually, you cannot just use large deviation. So maybe I just mention one sentence about how do we prove this lemma. Where is the lemma? This lemma. I mean, I couldn't really exactly prove the lemma here in this place. So this lemma says xk is not very small, it's exponentially small, and our, let me see, our proof, what's that? The proof is, again, this is the proof we use log-solver inequality, and I think, I don't know if one can remove this now, but anyway, this was the proof in the paper. We use some inequality called concentration inequality. This is a variation of log-solver inequality. It's some version of log-solver inequality. It basically says if you take a random variable, you take exponential of a random variable. This is imaginary part because, but you think about this, any real random variable then it's less than exponential of, instead of x, you take gradient of x squared, and then you take expectation. This is a variation of log-solver inequality. So, I mean, the log-solver inequality on left-hand side is f log f, and right-hand side is gradient f squared. But now if you take exponential, so you can imagine you get some exponential, and so it's some sort of log-solver. And then the important thing is this imaginary part of x, if you calculate this part squared, actually there's exact computation. This is exact. This part is exact calculation. And then you look at this calculation, you find that you almost go by itself, except you gain some factor of n eta. You gain a factor n eta because now we choose n eta has a log. So this part make this it almost like you introduce a small constant in front of it. And once you introduce a small constant in front of it, then you can do expansion. And that's the idea. And I mean, I'm not going to do this in detail. Roughly speaking, is we can compute each Cassini alpha, the exponential moment can be calculated. So once you introduce a small factor in front of it, then you can do the expansion for each one. This is just a rough idea. So I don't think I want to say much details about it. So the summary. So let me just say the summary. Roughly, I always say that we do the two things. One is we find the eigenvalue distribution we can control up to 1 over n, and then we can also do the L infinity norm of the eigenvector up to 1 over square root of n, and we have written all those with log has written, all those has no log has not been written, and then but of course if you want to really get this Wigner Dyson, this sign kernel, I think we are still quite far away. So thanks a lot. Thank you.
Questions or comments?
I have a comment concerning your second
Yes.
theorem. Well, somehow I wonder a little bit why in your proof still the eigenvalues of the random matrix
Yes.
appear. Well, to my opinion, what one really needs is only the invariant measure on the orthogonal ON or on the UN
Yes.
group. Well, since it's invariant against this, and to my opinion, it's not necessary really.
Oh, because
To-
it's
to
not
go.
GUE, you cannot do that.
Pardon?
You can do that only for GUE.
It's not invariant.
Oh, for what? From
If you
Is
just
this
have
for different-
independence, if you're not Gaussian, you don't have it.
You don't have a UN
You don't have
invariance.
the UN invariance
Ah.
anymore.
okay.
That's the
Okay.
problem. And so it's
Okay.
presumably there
Mhm.
in disguise.
Uh-huh.
Presumably it's still effectively there,
Yeah.
but,
Yeah.
but literally it's not there.
You want to say that this random is almost recovery in some sense, but I don't.
Otherwise.
This V4 norm, just to understand this V4 norm is just sum of these two components of these to 4 and then
One fourth.
root
One
of
fourth, yes.
1/4.
Yes.
So it would be, we expect that this sum over V to 4 is 1 over n, we expect,
Yes.
so it's 1.
Yeah.
So you have almost 1 over n but with logs.
I think now we have 1 over n without log.
Even without log.
Yeah.
Oh, so it's,
Yeah.
in principle, it should be 2 divided by n. We know that it should.
Oh yeah, no, I'm not saying that. I'm not the constant. It's just really.
But
I think I would like. I mean, maybe you have mathematically you first show that this object is first bounded before you can compute. So, of course I don't know this constant is 2 or whatever.
So if you can get the constant, then does that give you hope that you can get the GOE statistics too?
I mean this Dyson.
Yeah.
No, I think I mean we cannot really get a if we can get a constant, will it help? That's what you mean. Okay, this maybe I never thought about this. I just feel that because once you go down the scale, then it becomes harder and harder. So right now we still need the constant over n, but the constant has to be large. So it's still far from what you would like. Thank you.
Thank you.